Hello everybody. In our series of lectures on basic electronics, learning by doing, let us move on to the next. Before we do that, let us recapitulate as usual what we discussed in our previous lecture. You might recall in the previous lecture we discussed about a new device, semiconductor device, namely the uni-junction transistor. We discussed about the characteristics of the UJT, how you get a negative resistance region, and then how it can be used to design a relaxation oscillator, UJT relaxation oscillator. And then we also built, using couple of diodes and capacitors, a staircase generator, a waveform in the form of the staircase using the diode pump and the UJT. So the diode pump used diodes and the capacitors, and to limit the staircase wave we use the UJT to trigger the UJT and discharge the capacitor, etc. So you might recall all those that we discussed in the previous lecture. In this lecture I propose to discuss another important device, semiconductor device, which is called the silicon controlled rectifier, SCR as it is known as. It is also called by the name thyristor. So silicon controlled rectifier. What is a silicon controlled rectifier? Before we do that, let us just understand how it came about. If I have a simple N-type semiconductor, as you can see on the screen, if I have a simple N-type silicon semiconductor, then it becomes something like a resistor. Depending upon the doping, the resistance of this device will change, the conductivity will change by doping, and therefore the resistance. Now, so you can have either N-type resistor or a P-type resistor depending upon what you dope with. When you combine the two types in the same wafer, then you find you can have a junction diode. This we have discussed at the earlier stage. P and N can form together a junction, and it has got a very important property that only when it is forward biased it will conduct, when it is reverse biased it will not conduct, or it offers high resistance when reverse biased and low resistance when forward biased. So it is used for rectification to convert AC, which is a bidirectional voltage swing, to a unidirectional swing corresponding to the DC. Then someone thought, why not add one more layer beyond P and N? So when I add, I have a choice now. I can either have N, P and N as 3 layers, or P, N and P as 3 layers. Therefore you know immediately, you will recognize this is nothing but our familiar bipolar junction transistor, BJT. You have two junctions, the base emitter junction and the collector base junction. So you have J1 and J2, you have that emitter, base and collector. Similarly in the PNP transistor the configuration is the same, except that it is formed with P and P as the 3 layers. So naturally, if one thinks in the similar lines, you would find what will happen if I add one more layer. So when you think adding one more layer, you have a 4-layer device, a P, N, P, N device, and this is what we call the SCR, silicon controlled rectifier. So an SCR is basically a 4-layer device, PN, PN, and the P is called the anode, and the N at the end is called the cathode, and very close to the cathode there is a P region, and that region is usually called the gate terminal. So you have an anode, you have a cathode and a gate. You compare it with the normal diode, you have only 2 layers, P and N, and you have an anode and a cathode. So the anode is a P type, P side, so that when I forward bias, when I connect that to positive of the battery and the N to the negative of the battery, this will show low resistance. In the same way here, this is again an anode and cathode, that means it is also like a rectifier, but then you have an additional terminal at the P which is called the gate terminal. So what will the gate do? The gate should control the flow of current from the anode to the cathode. Therefore this becomes a controlled rectifier. Otherwise it is just like any other rectifier like the PN junction diode. You have an anode and a cathode, and it will conduct in only one direction. So, when I have a gate, then I can control when it starts conducting in a given input. So, we will discuss this in some detail later. So, basically an SCR is a silicon controlled rectifier. It is a silicon controlled rectifier because usually it is made out of silicon semiconductor. It is a rectifier because again it is going to be used for power control, and it is a controlled rectifier because you have an additional terminal called the gate which controls the power delivered to the load. An ordinary rectifier converts AC to DC, that is what we call rectification, and DC means unidirectional signal, current or voltage. A controlled rectifier controls the output power while rectifying. Let us try to understand little more, but you may be wondering why not germanium controlled rectifier. See, once the silicon came, everybody were impressed with the characteristics of the silicon semiconductor over the germanium semiconductor, because the leakage currents in the silicon will be much less compared to germanium, because in the germanium the band gap energy is smaller, 0.7 volts or something. In a silicon it is about 1.1 to 1.2 electron volt, and therefore the higher thermal energies are required for pushing the valence electrons into the conduction band, and therefore the leakage currents in such devices will be very, very small, and therefore it is very important for a switch. A SCR is basically a switch, and a switch should have low leakage current, because what is important in a switch is the on resistance and the off resistance. That is why we should have least leakage current, so that the on off resistances could be maximum and minimum as the case. So, it is basically a rectifier, it is a controlled rectifier, and it is a 4-layer device. So, alternate P type and the N type, 4 layers are there. This is what we should know. Now, why do we need that? Let me try to explain to you why we need this. If I want to control the speed of a fan, what do you do? If I want to control the speed, if you apply 220 volts, the fan will be running to the full, but sometimes we do not require the fan to run at full speed. So, what do? We have a regulator. I do not know whether you have seen that. Most of the time the regulators will be a big box. Nowadays it has come in a very small box, almost like a normal switch, and that is because of these devices which we are now discussing today, the silicon controlled rectifier and the rest of the things. So, usually what they will do is, because a fan is a current controlled device, it is a magnetic field which is producing the rotation effect, and therefore the magnetic field depends on the current. If I want to limit the current, then I can reduce the magnetic field, and hence the correspondingly the torque and the rotation speed and things like that. So, when I want to do that, the only way we all know from Ohm's law to reduce the current in a circuit is to increase the resistance in the circuit. So, in the old regulators, olden days, what we do is we have very high wattage resistors, and when you switch the speed, you can only switch the speed in steps. You will have normally, for example, full speed 5, 4, 3, 2, etc. So, when you come to 3, 2, 1, etc., the speed will be very, very less, because you have added more and more resistors whenever you switch, and thereby the current becomes less and less. So, that is the only way you can control the speed of a fan in a normal regulator that we had in the olden days. We are very rarely we see that, only in some old houses you would find. Now, what have you done? You have introduced a high wattage resistors in the path of the fan, the coil and things like that, and therefore the main current passing through the fan is now reduced because of the resistance introduced. But you should remember, this current will also flow through the resistance, and usually you have to use a large value resistance because you are using a large voltage, right, 200 volts, and therefore there will be an I square or dissipation through the resistor, that is an energy loss. If you touch the regulator after some time, you would find it will be very warm, because it is dissipating electrical energy, and you have to introduce it because you wanted a lower speed. So, when you want a lower speed, you have to introduce a resistance, and that naturally brings a loss of electrical energy by way of heat. You may find that this is a very small loss, you may think like that, but imagine a big auditorium or a cinema hall where there are hundreds of fans. All of them will have to have this type of a regulator for reducing the speed, and if I use those regulators, there are enormous amount of heat energy is dissipated over 3 hours or 4 hours, and if you now calculate what is the actual power or energy dissipated through all these regulators over a period of 1 year, for example, you would find this loss in electrical energy will be very considerable, and therefore you may be even paying for it without knowing, because the total energy consumption is what you are paying for. So that is now combination of the consumption for a useful energy in terms of the speed of the fan and the unused energy in terms of heat energy lost in the regulator. So you find it is not a very efficient way of controlling the speed of the fan. So what we do is we introduce a special device now, as we are entering into that, the silicon controlled rectifier. You would find the silicon controlled rectifier can act like a switch to switch on the power delivered to the load or the fan in this case at any instant you want, and thereby it can control the energy sent to that. To control this silicon controlled rectifier, we have the gate. I have already shown you the gate terminal, which is the control element, and you will still have to use a resistor to control the power delivered to the load, but this resistor now will come in the gate circuit, not in the main circuit in series with the anode and the cathode, but in the gate circuit between the gate and the cathode, and in that circuit it will come, and therefore the currents involved in the gate circuit are very small, usually of the order of milliamperes. So whatever resistance you put there, the energy dissipation in terms of heat energy in the gate circuit will be very insignificant, and therefore that will be able to switch the SCR at any required points, and therefore the power delivered, the large power delivered through the anode cathode circuit can be controlled by a small variation in the current in the gate circuit, which is in the order of milliamperes, and therefore energy dissipation in the total energy dissipation in the control of the fan will become very much reduced, and therefore you would certainly save lot of energy by using silicon controlled rectifier. That is why if you buy modern times any fan for industry or house, you will find they always give you a small regulator with a small knob which can be fixed like in the switchboard, and that contains a device similar to the silicon, which is actually a TRIAC. So it has got, and it can control the power delivered to the fan, and therefore there is good saving of energy, efficient method of controlling the rotation of the fan. So I gave an example of the fan, but you can have several examples, like in a big studio you have plenty of lights which are running to about 5000 watts, 1000 watts, 2000 watts, etc. for projecting onto the studio, and therefore you would find all of them will have to be controlled, the intensity will have to be controlled, and they all can be controlled by such devices like the SCR and the TRIAC. Right. So this is what I was mentioning to you. In a big concert hall, when you have more than about 100 fans, the regulation becomes inefficient if you introduce resistors in the circuit. So we try to use SCR. Now I have given you some simple configurations of the SCR. This is a very small SCR, normally in the TO5 package. This is TO5 package, like the transistor SL100. Some of this we have used in our earlier lectures. It will be like that, where you will have a tab at the bottom view. You will have a tab and you have 3 terminals, the cathode, the gate and the anode coming in the clockwise direction. So cathode, gate and anode will be the pins corresponding to this, but this is meant usually for very low power control. If you want slightly higher power, you have TO221 to TO225 packages and things like that, which are for higher currents. They can withstand 5-6 amperes, and the corresponding circuit symbol is anode and cathode. You see there are 2 diodes, and then you have a gate. This is actually the figure of an SCR. In the case of an SCR, you will have only 1 diode and 1 gate. So the package is something very similar to this, and you would also see when I show a demonstration the actual device. Now let us understand how the silicon control rectifier works. So, you have a PN region, 4 layer device, and that means it has to have 3 junctions between P and N, J1, between N and P, J2, between P and N again J3. So, J1, J2, J3 are the 3 junctions, and there are 4 layers. If I connect it to a large power supply with the plus connected to the anode and the negative connected to the cathode, and if I make it variable, what will happen to J1, J2, J3? Let us try to understand. To illustrate that, I have approximated this to a resistor here. So, if you look at this entire thing as a silicon block, then it has got a very specific resistance, and if I connect the resistance, at this point the voltage will be the applied voltage, full voltage, and if I go along the resistor at different points, you would find the voltage will be slowly decreasing till it comes to 0, because there is a drop along the resistance. We know that from Ohm's law. So, when I look at it in that perspective and see the p type is earlier than this n type, and therefore this should be more positive than the n type, and therefore this junction with the p type more positive than the n type should be forward biased. You all know that. Now, if you come to the J2, the n type is more positive compared to the p type, and therefore it will be reverse biased. And J3, where again the p type is coming before the n type, and it is at a slightly more positive voltage than this, and therefore this also will be forward biased. So, you find J1 and J3 are forward biased and J2 is reverse biased. That is a situation corresponding to this. Now, when I reverse bias this, immediately you can recognize what will happen. The situation you would find J3 and J1 will be reverse biased and J2 alone will be forward biased. J2 alone is more positive here on this side, whereas here this side is more positive, n type is more positive than p, therefore this is reverse bias. Similarly, this is also reverse bias, this alone is forward bias. Therefore, there are 2 junctions which will be reverse biased when you reverse the SCR. Right. So, the silicon control rectifier is an ordinary rectifier with a control element that I mentioned to you already. The current to the control element, which is termed as the gate terminal, determines the anode to cathode voltage at which the device commences to conduct. The gate bias may keep the device off, or it may permit conduction to commence at any desired point in the forward half cycle of the sinusoidal input, because we are always looking at input sine wave, how it is going to rectify into a DC. So, the SCR is a very widely applied AC power control device. There are other devices such as the DIAC and the TRIAC, which are also related to SCR. So, DIAC is a switching device, TRIAC is a triode AC. Triode means 3 terminals and it is used for AC, and therefore this is for full power control of the AC, or based on the principle of the SCR. Right. These are also, I mentioned to you, are known as thyristors, because in those olden days a similar device, which is a switching device, was used by using vacuum tubes. You have heard of the gas filled triode. The gas filled triode was called thyratron, and that is having a very similar behavior like the SCR, and therefore to remember that we call this, that was called thyratron and this is called thyristor, because it is based on semiconductor device. Right. So, the SCR basically is a true electronic switch which will make it conduct or not conduct, forward and reverse, something like that. Is why it is called rectifier. It can change an alternating current into a direct current and at the same time control the amount of power fed to the load. So, it combines the features of a rectifier and a transistor to control, active control. If you look at the NPN device, this is P1, then the N region I have separated as N1 and N1 prime, and then P region also I have separated as P2 and P2 prime, and then I have the N2 prime, N2 region. So, if I now look at it, you find the PNP is actually a transistor, NPN is also a transistor. Therefore, they are 2 transistors separated and then they are connected internally, that is what it is. So, you can have the corresponding circuit diagram I have shown here. There is an emitter here, there is a collector, and the collector is connected back to the other transistor, and the emitter of this second transistor is connected to the base of the first transistor. Therefore, there is an internal feedback here between the two transistors. Ultimately what you have is an anode, you have cathode and a gate terminal, that is what you have here. So this is the equivalent circuit. So when you do a circuit analysis, which I am not going to do here, you would find this model comes out very handy for understanding the behavior of the SCR. I have shown an actual SCR here, the 4-layer device and the corresponding symbol. You can see there is only one diode here, there is only one diode and a gate, anode and cathode, and the gate is very close to the cathode, that is what you should remember. And the easy direction of current flow is from the anode to cathode, that is why the diode symbol with the arrow pointing towards the cathode is shown here. So this is a circuit symbol, that is what you should remember. Now let us try to understand the construction. The PN junction is added to the junction transistor, and the resulting junction is the 4-layer device of the silicon control relay. Right. In the normal operating condition, the anode is kept positive, I told you, for forward biasing with reference to the cathode, and the gate normally will be kept at a low potential, low positive potential. Right now let us assume if I do not give any voltage to the cathode, to the gate, then what happens? If I keep on increasing the DC voltage connected between the anode and cathode, you would find at some critical point which is similar to the Zener diode, Zener breakdown voltage, the thyristor will start conducting due to the forward breakover voltage. Just as in the Zener diode it is in the reverse bias, you have when you exceed a maximum voltage limiting voltage, then you find it starts conducting continuously due to avalanche effect. In the same way this also will start conducting beyond some voltage, that we call the forward breakover voltage. Let us see the characteristics. Right. So the SCR basically has got two states, one state corresponding to when it is turned on, so it conducts heavily, and the other one corresponds to turning it off when there is no conduction through that, and the SCR behaves like a switch in that sense. It can either switch on or switch off. There are two ways to turn the SCR, that is what I was mentioning to you. The first one is to keep the gate open and increase the supply voltage between the anode and the cathode till you reach the breakover voltage or the breakdown voltage corresponding to the avalanche breakdown. The second, which is more common, is to turn it on by using a current through the gate terminal. Then you would find you may be able to bring down the breakdowns condition even before you reach the breakover voltage, and therefore you can make it conduct at any other voltage below the breakover voltage. That is the advantage of the gate terminal. Right, you can turn on by using the gate terminal, but what about turning it off, the switch? When you want to turn off, you cannot turn off using the gate. That means if I cut off the current from the gate, will it switch off? No, it won't. So the gate can help only to switch the device on, but it cannot help in switching it off. That is what you should remember all the time. So how do I switch off the SCR? The only way to bring the SCR to an off state is to bring the current flowing through the anode and the cathode to a value below a limiting value called the holding current, IH, as you can see. What is the holding current? It is a current which I should hold, above which only it will be in conduction, and below which the SCR will come into off state or non-conducting state. How to reduce current to the below the holding current? There are two ways again. Either you can reduce the voltage you have applied between the anode and voltage, then automatically by Ohm's law the current also should reduce, or keep that voltage constant by introduce a resistor in the circuit of the anode and cathode and increase the resistance so that the current keeps coming down, and when it comes below the holding current IH, then the SCR will again come off. So these are the various things that you should remember when I look at the SCR. Now I have shown you the characteristics of the DC characteristics of the SCR. You can see when I do the forward biasing, that means I should, this x axis is on the voltage, y axis is in the current, and now when I keep going here along the x axis, you would find if I do not have any gate current, it will come up to this point which is marked here as VBO, which is called the V forward breakover voltage, and at that stage the SCR will start conducting. Once it conducts, it means it is switched on. So the voltage across the SCR will be a very small voltage somewhere here. So this is a very small voltage. This should be something like 100 volts, 200 volts, but this voltage will be almost close to 1 volt. So it will come quickly to this conduction region, and if I now keep increasing the applied voltage, you would find the current will increase like a normal diode, right, with very little change in the voltage across the device, but the current will increase enormously depending upon the voltage I apply. That this shows that it is on the conduction region, it is conducting now SCR. Now if I apply a gate current Ig1, Ig0, Ig2, Ig1, etc., then you find depending upon the magnitude of the gate current, I can switch this off much below the breakover voltage or still below depending upon the magnitude of the current. These are different points at which it will break, and then it will come over here. Now when I want to switch off, then I will bring down this current, anode cathode current, to a very low value below a threshold which is called the IH, or the holding current. When I bring it below the holding current, then quickly you would find from this point it will come out to this point. If I only increase the resistance in the circuit, the voltage will remain constant, and therefore the voltage will come. So now if I apply 200 volts, and if the SCR is on, across the SCR there is only 1 volt. So what happens to the rest of the volts? The 199 volts now will have to be applied across the load that you have connected in the circuit. So thereby the power is now delivered to the load. So that is what we see. And what you have on the left side is the reverse bias. You find it is like a normal Zener diode, except that this reverse breakover voltage will come too far away compared to the forward breakover, because there are 2 junctions now which are reverse biased. So after that it becomes something like an avalanche effect, and so you have a reverse blocking region in this region and reverse breakdown region beyond that point. So this will be the characteristics of a silicon controlled rectifier. How to obtain the characteristics? You can see I have got a circuit here. I am now going to show you with a low voltage power supply, so that even that you can reasonably understand. Even though you can put here 100, 200 volts here, I am now going to use a 30 volts power supply which I have been showing to you all the time, and I have a current meter. So because the voltage is small, the current is going to be small in milliamperes. So I put a 0 to 10 milliampere current meter, and I have put a potentiometer which I will 1 megohm potentiometer, which I will keep it in 0. That means this resistance is not included initially, and I have put some safety resistance 4.7 kilo ohms here, and this is the SCR, and the cathode is connected. There is a voltmeter here between the anode and the cathode of the SCR to measure what is the voltage across the SCR. And if you look at the gate current, gate side, I have connected a 5.6 kilo ohms in series, and a current meter 0 to 500 microamperes, and 0 to 5 volts I have put it into a potential divider with a 10k resistor, so that I can change this voltage and find out at what current the output voltage the SCR triggers on, SCR starts conducting. So you would find if I keep it at 30 volts, then of course 30 volts is not enough to break this SCR. The forward breakover voltage will be some 200, 300 volts. So it will be very difficult to make this conduct with 30 volts, and therefore I have to give a gate current. So now if I move this wiper on the 10k potentiometer, you would find at some current you will have enough current to forward bias that junction. Therefore there is immediately enormous conduction here, and therefore SCR will be triggered on. Once the SCR is triggered on, this voltage you would find, which was till that time 30 volts, will suddenly come to very low voltage of nearly 1 volt, and the current will also show a large value here because it is now conducting. Now if I remove this gate current by switching off this 5 volts power supply, you would find still the voltage here which will be around 1 volt, this current will be large depending upon the resistance. So the SCR cannot be switched off by switching off the gate current. That is what I want you to realize. So if I want to switch off the SCR, what is that I should do? I should reduce the current below the holding current, this primary current, the anode current. So what I do now, I have this 1 mega ohm resistor, I will start increasing the value of the resistance here till the current comes to a very minimum value corresponding to the holding current. Immediately at that time you would find this voltage, the moment it comes to off state, this is off, and therefore the entire voltage will appear across the SCR, and this voltmeter will show 30 volts. So this is what I want you to recognize as the DC characteristics. Now I will go over and show you the demonstration of the voltage. Before that, I want to recapitulate some of the important points, terms. Breakover voltage I explained to you already, it is a minimum forward voltage with gate open, with the SCR starts conducting heavily. Peak reverse voltage is a maximum reverse voltage between with the cathode positive that can be applied to SCR without conducting in the reverse direction. Then holding current is the maximum anode current, gate being open, at which SCR is turned off from the on condition. Forward current rating, circuit fusing, etc. are all also important point, and I am going to use an SCR which is called C106. This is a TO225 AA package. You have got 3 leads, and they are A, K and G. The leads are shown here. The first one is the cathode, anode and the gate, and it is actually capable of handling 4 amperes of current, and 200 to 600 volts you can apply between the anode and cathode. These are the characteristics. There are few more characteristics here. The most important point in all devices is that one should learn from the data sheet. You must look at the data sheet, because data sheet is the data given by the manufacturer. He gives you all the limits within which this device can be operated. Therefore one should carefully go through that, and you would find it is also 200 or 400, 600 volts you can operate this device and different variations, and the RMS current is about 4 amperes, etc. All the important details will be available here. One should go through and try to understand the characteristics of the device. They also give you the characteristics, how it will look like. You can see exactly similar to the one I showed you. The characteristics is shown with demarking correctly the various regions of operation. Now with this, let me go and show you an actual demonstration with an SCR, and we will try to see the characteristics. So I want you to look at the circuit here. It is the same circuit which I discussed. You have a current meter for measuring the anode current. You have a 1 mega ohm resistor. This is the 1 mega ohm resistor that you have in the circuit. You have this 1 mega ohm resistor here, right. This is a 1 mega ohm resistor which comes in the circuit here. Now let us go back to the circuit, and you have another 4.7 K resistor, and then this is the SCR, the C106 TO225 package that is here, and then the gate and the cathode is connected to ground, and there is a voltmeter. I have a voltmeter connected there, and the gate I have connected some 5.6 kilo ohms and a small 0 to 500 microampere ammeter, and there is a 5 volts potentiometer with the 5 volts applied, which can vary the voltage, and thereby I can reduce the current, change the current is what I have. So exactly the same as the one which I explained to you. Now the actual device is here, and the resistors are all connected and the wiring is done. This is for measuring the gate current, and this is measuring the anode to cathode voltage. Now it is, I maintained it around 19.8 or nearly 20 volts, and this gate current is almost 0 now. There is no gate current. Now there is also another multimeter here which is measuring the anode current, the anode cathode current. It is in milliampere position, and it is very low, 0.2 something. So now what I am going to do is I am going to vary this position, so that I will apply larger and larger voltage. It is now in the minimum position. Now I will increase it so that there is a current. I want you to observe this ammeter, that microammeter for the gate current. You will observe this microammeter when I am changing. When I get a current here, you kindly, as I have kept these two close together, so that when the current here becomes large, the voltage here will become less. That means the SCR has broken down, it has come into conduction state, and therefore this voltage will become less than 1 volt. This current will, when it reaches a critical value, this will happen. So I want you to observe these two. Now I am going to change the gate voltage so that the current starts building up here. So please observe those two. Please observe only those 2 meters. you observe only these 2 meters, okay, when I change, yeah, only the 2 meters you should see. Now I am, oh, now you can see there is a large current of nearly 300 microamperes or so is flowing, and now what has happened here, it has come to 0.5 volts. So when the large gate current triggers the SCR is on, so the 20 volts that we applied now has become 0.5, which clearly shows the SCR has come into conduction state. This is the gate current. Now I am going to reduce the gate current, keep observing only here. Now see what happens. I reduce the gate current, so I have reduced the gate current to very low value, as you can see here, almost 0, and still this is conducting, no, this still it is only 0.5 volts, that means the SCR is still conducting, right. So if I want to bring the SCR into on off state, the only way I can do is by increasing the resistance in the circuit. Therefore another potentiometer I am going to vary. Now I want you to look at this current here. Now the current is decreasing, that because I am increasing the 1 megohm resistor in the circuit. So when it comes to very low value, then suddenly you will find it will become 0, that means SCR has come into off state. Yeah, I am decreasing now, 24, 23, 19, 17, 14. So very low value 0.015 milliampere it has come. Now if you look at the voltmeter, it has come back to 21 volts. So the SCR has come into off state when the current came below the holding current. The holding current is about 7 milliamperes or so. When I bring below 7 milliampere, again this has come to on state, and then it is showing a 20 volts. Okay. So we saw the DC characteristics of the SCR, where we applied a DC voltage on the gate, and we applied also a DC voltage on the anode to cathode, and then as I increase the gate current, the SCR came into on state. When I reduce the gate current, the SCR was still on the on state, and when I finally reduce the main current below the holding current, the SCR came into off state. Now SCR is not used for DC, we have to use it in AC. The great advantage of using SCR in AC is, in the AC signal, every time the frequency of the AC signal that we apply is 220 volts, 50 hertz, 50 hertz is the frequency. That means what? The voltage goes plus 220 to minus 220 volts every time, to 50 times in a second. So when the voltage goes sinusoidally from 0 to 220 volts and back to 0, automatically the anode to cathode voltage is brought below some value, minimum value, and therefore below the holding current, and therefore the SCR will come into off state. So when I switch on the SCR during the positive half cycle, while it goes through the negative half cycle, automatically it goes below, and therefore the SCR comes into off state every time without doing any effort from our side. So if I now make the SCR conduct at a particular point, you would find in every half cycle the same point, that is the current required at the instantaneous voltage for the SCR to switch on, and therefore the SCR will switch on only at that voltage. For example, if I keep a gate current corresponding to 100 volts on the anode to cathode voltage, then you would find SCR will always trigger only at 100 volts. After that only the voltage will be applied across the load. So what you get across the load will be a distorted sinusoidal output. For example, I have shown you this circuit here. I have put the gate current also from the same AC. The AC is connected to the anode and the cathode with the load here, and I have also connected a potential divider and derived from this, and I put a diode, therefore it is rectified. So I have a DC current here flowing, which is also in the form of sinusoid now. And now what happens when I increase this position, you find it can trigger at, say for example 90 degrees. In this sinusoid this corresponds to 0 volts, this corresponds to 90, 180, 270 and 360. So that is corresponding to one cycle. So when I take the one cycle, you find at this point at 90 degrees, if the current is sufficient at 200 volts, it will break down. So beyond that you would find the voltage will become 0.5 or less than 1 volt across the SCR. The rest of the voltage 200 minus 1 volt is applied across the load, and therefore load gets the power delivered. So the shaded area is actually the voltage applied across the load, and that corresponds to the energy delivered to the load. And when it comes to 0, automatically the holding current comes to very low value, and therefore you find SCR comes into off state. And in this region the breaker voltage is very large, it is reverse biased SCR, and therefore it is not on at all. And again it is not on till I reach the same point, 90 degree point on the next half cycle. That is a current that I have kept here, and therefore again it conducts. So like that you find for every half cycle only a portion of the half cycle is delivered across the load. If I reduce the current, I can make it switch on here or here. That means in any angle between 0 to 90 degrees I can switch the SCR on, and so but I cannot go beyond 90. When I want to go beyond 90, you would find there is a corresponding point below 90, and therefore SCR will trigger here itself, and it will not wait for this to come when the gate current is available. And therefore if I want to control more than 90 degrees, then I have to not use a DC like this, but I should use a pulse. If I use a gate pulse, then you find I can shift the pulse to this point or this point, so that it is available only at that instant, and at that instant whatever is the magnitude of the gate current, for that the voltage will be applied at this point, and therefore it will trigger at the point, and therefore I can vary this angle, conduction angle, by more than 90 degrees if I use pulses on the gate circuit. So that is what is shown here. I am applying different pulses, and therefore I can shift the pulse with reference to this 0 point anywhere, and correspondingly make this conduct at any point. For here it is conducting below 90 degrees, beyond 90 degrees, here below 90 degrees. So you find the area here is different, but this cannot happen in different cycles, it has to be the same, and therefore these pulses will have to be synchronized with the AC pulse, and that is one of the very important difficult parts of the thing. We can also do it using other means. For example, what I have shown is a very simple thing which I also show a demo. I have applied voltage source here, and I have got a RC combination here, resistance and capacitance, and the RC combination can give you a phase shift, and therefore that phase shifted sine wave is what I am applying after rectifying through the diode as a gate current. So thereby I can change the AC convert it into DC, a rectified DC that is coming through the gate, change the position by changing the phase shift by using this RC combination, and thereby I will be able to control more than 90 degrees on the gate pulse. And I have put a lamp here, so that this is one of the very important applications. This is a lamp is a non-inductive load, therefore it is very simple to show. I am showing a 12 volts 10 watts lamp, auto lamp, and you would find this intensity can be controlled by controlling a potentiometer which is in the gate circuit, not by a potentiometer in the main circuit. If it is in the main circuit, the dissipation will be large. If it is in the gate circuit, the gate current is milliamperes, and therefore dissipation will be large, very small, and therefore I will be able to control the intensity by controlling the amount of energy delivered to that by switching the SCR at some desired points from 0 to 180 degrees. That is what I am trying to do, and we will also see the waveform on the CRO when I do that. So I would like to show you this demonstration before I go into the other aspects of SCR. So I want you to see the circuit here for the AC characteristics. You have a input AC, this is actually got from a transformer, high current transformer, and I have a 2 RC network, and then this is the small load here, this is a lamp, and then the SCR, and this is the CRO. I measure the voltage across the SCR through the CRO so that I can see the waveform and the current control, the angle control. and the gate current is derived from the RC network. Therefore, there is a phase shift here by 1 by omega CR, and that is being applied after rectification, because it is still AC. I rectify it using this diode and give only the DC current at the gate, between the gate and the cathode. So, this same circuit is wired here exactly in the way there is a capacitor and the resistor, and there is also the diode. And what you have here, I want you to look at here, is a transformer. This is a transformer. The input is a 220 volts mains, and the secondary is around 18 volts or so, and that is connected through a auto lamp and a small resistor here to reduce the voltage. And this is the resistance that you find in the circuit. This resistance is mounted on the panel here. So, this is the resistance which is changing the phase shift, RC phase shift, and when I change this, you would find intensity of this light will become different. I can control the intensity. Now, I want you to look at the lamp. As I change the phase shift, you find the intensity is increasing. That means more, and the SCR is triggered even before, and more voltage is applied across. Therefore, now it is very bright. So, I can change the intensity of the lamp by changing a potentiometer which is in the gate circuit. That is what I am trying to do. That means the energy dissipated in this potentiometer is very small, because it is in the gate circuit, which is only handling few milliamperes of current. But this voltage, the voltage applied across the load, is a large voltage, and that can be controlled very easily using this arrangement. This is the knob that you see in a fan regulator also, but the circuit there will be slightly more complicated, because it is an inductive load. You have to use some filters, because what you get ultimately will be a pulse of different things. Now, I want you to look at the oscilloscope figure. Initially, you find the entire sine wave is seen. Now, when I change the potentiometer, you find it is triggered at this point. Therefore, it has now this portion, small portion, is a portion which is actually going into the let me arrest now you can see, if I increase the potentiometer, you would find the horizontal portion increases. That means it is now triggered almost 90 degrees. Now, it is beyond 90 degrees. Now, you see, one is this amount is across the SCR, the rest of the voltage is applied across the load. Therefore, that should correspond to very bright lamp. So, now you can see the lamp is very bright here also. So, this corresponds to this signal. So, you find it is only triggering even at this point, when it will be around about 5-6 volts, then the entire 18 volts, this peak entire voltage is applied across the load. Therefore, the load is very bright. If I now increase that, you find this side it is very small, it is beyond 90 degrees, and therefore, the voltage applied across the load will be very small. If you look at the intensity of the lamp, now it is very small. So, the energy supplied to the load is changed by changing the angle of conduction, and that is what is clearly seen here. Now, it is almost full bright, and then if I reduce it, you can see the variation can be changed corresponding to the waveform that you see here, right. So, this is corresponding to the AC control of the SCR. So, you saw when I use AC, I am able to control the actual power delivered to the load, in this case a lamp. Now, the most important thing is, because I have used only one SCR, I am able to get only a half wave rectified signal across the load, and that half wave rectified signal is can be now controlled. The energy delivered, which is normally the area under the graph, can be controlled by changing the switching at different angles along the half wave rectified signal. So, that is a principle of controlling the energy. Now, what happens when I want to go for full wave? Many of the fan and other devices, they require full wave. So, full wave AC control, if I want to do for full wave, then I have to use 2 SCRs perhaps for both the things. Instead, what we do is we go for what is known as a TRIAC, that I already mentioned to you. You see on the screen, this is a TRIAC, triode AC. when I use a triode, you again a TRIAC, again you have same two anodes A1 and A2. There is no cathode, because you know the signal can be both this side positive, this side negative, and this side positive, this side negative when the AC changes, and therefore both are called A1 and A2 anodes, and you have a gate. You have a single gate only. If I use two SCRs, I will have two gates which have to be controlled. In the TRIAC, it is cleverly designed by controlling the layers and all that. Therefore, you find only one gate. By controlling it, you would find you can control both half of the AC signal, make it to conduct at any desired angle. If I do it at 60 degrees on the positive cycle, again at 60 degrees in the negative cycle also it will trigger, and therefore there will be a corresponding pulse both on the negative side and the positive side. So the characteristics of a TRIAC is something like that. Just as you have a forward bias characteristics, you also have a similar reverse characteristics, exactly identical reverse characteristics, and rest of the things are all same. You can have different gate currents, you also have a holding current, all those things are there. So this is a characteristics of a TRIAC briefly, because it is a basic electronic course. I don't want to go into more details of the actual construction and design. This is the equivalent circuit of the TRIAC. I would like you to read little more on those things. And when I have a TRIAC, this is a TRIAC of symbol of a TRIAC, you have two diodes in both directions, you see. So this is anode for this diode, and this is anode for this diode, that is why it is called A1 and A2, and you have single gate, and the circuit is very similar to what we have seen already. You are controlling the gate voltage, thereby you see the area under the graph is what you get as the energy supplied to the load, and you find both sides you have this. So by moving this potentiometer, I will change the conduction angle here from 0 to 180 degrees. That means I can make the entire energy available at the load or no energy available at the load, but by controlling the current in the gate, that is what you should recognize, and therefore we get enormous energy saving in terms of the loss that can happen if I introduce such devices in the main circuit. So this is a TRIAC, and there is also another device called a DIAC, which is again a switching device, and that is shown here, and this is also combined along with SCR to control, along with the TRIAC to control. So you may also have sometimes TRIAC and DIAC in one compartment, one device which is called a quadrac. But more important, SCR applications, SCR can be used as a static contactor or as a for power control, about which we talked about. It can also be used as a speed control for DC shunt motor or overlight detector, about which I also mentioned. There is also another variation of the device which is called light activated SCR. Light activated SCR is sensitive to light. Instead of the gate you send a current, you send a light on the SCR, you would find the resistance will change, and thereby the gate current will change, and so it will be activated. So the state is controlled by the light falling on the depletion layer, and the normal SCR gate current turns on the device. In a light activated SCR, instead of having the external gate current, light shining on the device turns it on. This is very useful in light operated switches and things like that. Lastly, we already studied about UJT. One of the very important applications of UJT is to apply control pulses on the gate of the SCR. So I can combine an UJT and an SCR like in this shown in the circuit with an RC network, right. I take the rectified output and connect it to the B2 and B1, and I put a resistance through an RC network and connect the gate to the emitter of the UJT to this. Therefore, depending upon the pulse, the eta VBB plus VD will be reached here, and therefore that will discharge the capacitor. Therefore I will get a pulse here. This pulse can now trigger the SCR at any given point. Thereby by changing this resistance, we would find I will be changing the phase, and therefore I will be changing the conduction angle of the SCR very easily. This circuit is something which you can try in the lab and see how UJT with a relaxation oscillator type of a combination can provide pulses to control, and the SCR can be controlled. I have used the power supply from the same AC, then only it will be very well synchronized. That is why I have used here, and I am using this RC for phase shifting the pulses that I get, and thereby I will be able to use the SCR to control the UJT to control the gate of the SCR. there are different types of circuits available for controlling the SCR. So, an SCR is a very important device which is used for power control applications, and the variations of the SCR like the TRIAC, DIAC and the light activated SCR are also very useful in different application circuits. Thank you very much.